Hello, everyone. My name is Greg Nazario. I'm a founding engineer at Aptos Labs. Sorry for the delay. I had some headphone difficulties, but I'm here today to talk to you about the Move language on Aptos and some of the differentiators it has in the space and how it accomplishes them. So what is Move? Some of you may be familiar with other languages like Solidity on different blockchains, but Move was actually built for the Diem blockchain, which was at Facebook, built upon the idea that there were sort of missing pieces to smart contract development, especially after seeing the number of hacks and errors made in other languages. So the whole basis of building Move was to ensure that there's a smart contract language built with principles of being simple, secure, safe, flexible, and formally verified. It had a bunch of design goals in mind that was associated with this. First of all, that data safety is important by an ownership model. This is similar to other languages like Rust, where it prevents memory leaks, double spends, losing resources that you expected to store somewhere, instead you just drop them forever. This provides type safety that lets you prevent a whole slew of attacks and a whole slew of bugs that cause a lot of financial loss that we've seen in other blockchains. One of the other things was the simplicity. Having a language that's very complex makes it very hard to ensure that there are no bugs, ensure the security is good, and making sure that you can actually audit the code. So it was built from a simplistic standpoint at first, and a lot of people get kind of lost in that, but we'll go over some of that later. That simplicity actually was allowed to make it transfer over into having a bytecode virtual machine, wherein because it's simplistic, you can have a full type-safe VM that verifies the correctness at runtime. Unlike EVM, that it might not actually be able to do that, this actually can stop a bad program from making sure that the bytecode is actually correct instead of just crashing because the bytecode is wrong. And additionally, adding formal analysis semantics, which allows you to mathematically prove the correctness of programs, ensuring that actual preconditions and postconditions apply throughout the entirety of a program. I first want to talk a little about the two main storage models on Aptos. A lot of people ask about the way that different things are stored and built upon Aptos, so I'll go over them. The account model here, as you can see here, is a simple solution where data is indexed by type. It can be parameterized, where you have a specific generic type that's put on it, but it's easy and simple to have that resource ownership. So in this case, you can see the first account has a single resource named account. So I can access it by saying, I want to borrow this global resource from this account. Very simple. But then if I change the address that I want to borrow the global resource from, I can borrow it from the second account, where I can access that one account. So at that point, you have what is a map of all the resources in this global storage, accessed by address. So additionally, you can see in the second account here that we also have in addition to the account resource, we have a coin store resource, which is specific for Aptos coin. So having these different resources, I can access them individually and interact with them. And it's very logical and simple, where you're mapping one resource to one name under one address. Very simple. But then we wanted to build off of that and build some flexibility to it, because we found that this works for most cases, but sometimes it's a little bit easier to think about things in a different model. So what we added was an object model that allows for flexibilities around how developers can choose which works best for them. In this particular case, we built off the account model to build the object model, in which each object is basically an account. The difference is that objects have ownership. So they have this resource called object core on that account, and from there it has an owner that's associated with that. That allows for you can reference the object directly with its address. Additionally, you can have specific owners of those pieces of data, allowing flexibility of moving data around easily with low gas costs, which is really nice. And additionally, with resource groups that was added on top of this, it allows for resources to be extended. So now, even though you have a fixed piece of data, you can add extra resources onto it. And now you treat this entire container of resources as one thing that can be moved around with variable data inside of it. Now, I'm going to go over a certain use case that I have in this diagram. One of the main driving points of this object model was working through an NFT standard. The NFT standard was a little bit complex on Aptos. Working through the account model, you have to make sure that you have the right person, access the right data, and building off of that. Versus here, you can see that I have two objects. The object on the left is our collection, and the object on the right is a token. And the token refers back to the collection, so now you know that if you have a token that it's in the collection. And then the collection has an owner, the creator of the NFT, and each token would have a different owner. So it keeps track of the owner in each token. That way you can have hundreds or thousands of different owners, but one creator, and it all is referred back to each other. This allows really great scalability and parallelism that isn't necessarily taken from the account model if everything is in one place. This also, as you can tell, is easy for composability. We look at the objects, and you look at the right object, and it has the token owner is an address. I could have another token that is owned by that token, and then when I transfer that token, it simply transfers all of the tokens together. So this composability lets you put things together, move things around in a very simple way that doesn't necessarily have this centralized storage, but instead is split out across multiple different areas. So now I want to go into the way that code is distributed on Move. In Solidity, you often have to deploy a contract, and you have to go to OpenZeppelin and get yourself a NFT contract, and then fill in the data that you want, and then publish a new contract. Or you want to make an ERC20 token. You make the ERC20 token, change some values, change the name to what you want, and then you post that onto the blockchain. But the problem there is I'm copying and pasting the code between every single contract. In this case, on Move, you actually deploy the code in one place, and it affects resources in other places. So that makes really easy code reuse and separation of code and data that allows you to build composable modules. So a piece of code can refer to another piece of code, and you can upgrade the original one or upgrade the one on top to build a bunch of different pieces on top. One of the good examples here is the coin module in the Aptos framework. You can create a fungible token in just, I think, about 2 or 3 lines. You basically have to deploy a struct that defines your coin, and then at that point, you can just call the already existing coin register function to create that coin, and then it will affect all other accounts that use it. So at that point, you just have one call to make a coin. Really simple. Takes like a couple minutes if you don't know what you're doing. This prevents you from having a bad implementation, because before I said, if you're copying a contract around and let's say you accidentally change something, you could have some bugs, some errors, versus here it's shared code. So in the event that there is a bug, you can update that one place and it will update all other contracts. So in the event that there is something wrong with the coin, you could deploy it. Or if you want to add an extension, like for example, originally it did not register and create a coin store and account on transfer. That was added later on through the code upgrades. That's how I transition into talking about our code upgrade system. So on Aptos Move, code is published via packages, which are collections of modules and contracts. They can be simply upgraded by just republishing the contract over and over again. So if you decide that you wanted to change something or you found a bug, you can simply upgrade the contract. That comes with some compatibility rules to prevent you from deploying something that might break another contract. As I mentioned in the previous contract page, that modules can be called by other modules. So the compatibility rules prevent you from changing the function signature or the arguments and the outputs of a function that's public because another module may be calling it. That prevents bugs that might be called from having these contracts that are built off of each other. Additionally, packages can be set as upgradable or immutable at creation time. So, and you can actually upgrade them from upgradable to immutable. That way it gives you the flexibility that you want to be able to upgrade the contract later or prevent it from changing specifically for whatever use case you want. Additionally, the source code is co-located with the code. So this makes it really easy for people to be able to audit your code, make sure they know what's going on, and in the event that the source code you don't want to be up there, you can turn it off and it won't be uploaded with the code. That way, you decide that you don't want people to see all your really bad comments that you have in your code, it's no longer there. Also, on Aptos Move, a ton of systems around testing formal verification tools. So the unit testing system allows for rich, easy testing that allows for error conditions, checking different cases, and being able to truly test your code in a sandbox environment that isn't necessarily on the blockchain. This is a little bit nicer than having to have to deal with end-to-end tests, but end-to-end testing also is a choice where you can deploy a local testnet specifically to do that. With the unit testing comes coverage, which a lot of people like in other languages. The ability to have a coverage tool and tell you the percentage of coverage is very useful, including even one of our centralized order books on the blockchain is 100% coverage. Akania, the guy who works on it, he loves testing. He's got 100% coverage on his code, making sure that every single line, every single branch is covered. But sometimes you can't actually test every possible input, every possible ability, which is why the Move Prover exists. So the Move Prover allows you to do formal verification, which sometimes this goes even over my head, but it allows you to mathematically prove that there is no case in which something will happen. There's a precondition, a postcondition, or an invariant, which is something that would go all the way through. So in the case of a coin transfer, I might say, hey, it will abort if I don't have enough money to transfer the function. So that's a good check there, as long as it works with that. Additionally, documentation generation is built into the code base. So we actually have a document generator that is built for the entire framework, and you can build it for anything else as well. You just put the inline doc comments and run this command, and boom, you have a giant markdown page you can deploy and show people how to use your code. And additionally, as I was talking about before, since the bytecode is on-chain and easy to find, you can use a decompiler to verify your code, as well as provide that ability to see things from a transparency and security standpoint, and ensure things haven't changed. And there are much more to come in the next couple months around linting, formatting, and other things. So only on Aptos. I wanted to talk a little bit about the things that are only possible on Aptos with Move. We support the full Move language with flexibility between two different models of the account model and the object model, as I said before, allowing developers to choose which one works best for them, giving trade-offs for parallelism, performance, ease of development, and providing that ability to choose what you want. That's what we're mainly trying to do here, is make sure that the flexibility is there for you to build it in the way that works for you. We have rich framework libraries around things like autonomous accounts, which are similar to EVM contract accounts, where you can deploy code to it, make the account immutable, or even throw away the key, say you can't access it again. And then that contract can hold resources, it can have the code, it can do everything separated on its own. We have a bunch of great storage tools around things like smart vectors, smart tables, and these allow for great scalability of data. In the event of things like you have a allow list of 10 people, you can just simply have a list, a vector of those. But when you have 1,000, 10,000, 1 million, that's when it starts scaling, when things start breaking down. So these libraries provide the ability to easily scale and make sure that, hey, you decided today that it was only going to be for 10 users or 10 games or 10 whatever. Now it perfectly scales to 10,000, a million. And also we have a digital asset and fungible asset standard libraries that allow for easy composability of these pieces together. So you can make anything fungible if you want. You can add onto a token that's a fungible asset and add in extra pieces to it. You can take a digital asset as an NFT and make it soul-bound, make it not soul-bound, change it at any time that you want. And that flexibility allows for tons of building and tons of different opportunities about the creativity that we can get from the builders in the space. And everyone's favorite thing is easy programmability for parallelization. Block SDM provides dynamic parallelization without having to deal with declaring your dependency up front. So you just program, and it will work on its parallelization itself. You don't have to deal with anything at all. You can do some things to optimize the parallelization. And additionally, we built aggregators specifically for that, being able to sum up values while still being parallel. Because normally, if I take a number 1 and I add 1 and then add 1 and then add 1, I need to ensure that all of these are serial, because I need to make sure it's 1, then 2, then 3, then 4, then 5. Aggregators takes that to the next level, which lets you sum those values up without having them lose the parallelizability in block SDM, and many other cases that will be super exciting to see there. We also have sponsored transactions, the ability to sponsor another person's transaction. Makes it really easy to be able to pay for what people often call gasless transactions. On-chain and off-chain multisig, we have the flexibility there to allow you to do both. They're both native, and it's great for securing contracts like DeFi and other things. Move scripts, which allow you to call multiple function calls of anything you want and compile it together ahead of time before you publish it. This allows you to be able to not publish a code package online, but instead dynamically create other calls that you might want to make and publish them and run them. So in that case, I want a function that says, hey, I want to always transfer 50% of the money in my wallet. You can make a script for that rather than having an actual function for that. Decompiler as well, only on Aptos, as I talked about before. Provable on-chain randomness, which we're just testing out right now in our RandomNet hackathon, providing provable on-chain randomness that can't be biased. It's great to see, as well as you can't be modified by other people, and allows you to keep on calling it over and over again to get more and more random values across different functions. And then keyless accounts and passkey authentication, which we talked about fairly recently, being able to have different types of account abstraction where you can have keyless accounts and log in with your OIDB provider, such as Google. And then you can also use passkeys from Google, Facebook, you name it. The future of Move. So right now, the team's working on a brand new compiler. Once that brand new compiler is working, we're going to have some great new features for the future. Receiver-style functions. A lot of people complain about the fact that, hey, why can't I just call vector.length, which is very common in pretty much every language. That's going to come up soon, along with user-defined abilities, being able to say, hey, I want a trait that says, I only want to accept things that can be ordered into the sort function. That is coming up in the future. Resource access control, preventing different resources from being able to access others and having fine-grained control there. Enums are a big ask for function feature that's coming up. And public structs, being able to use structs across all different places, and much, much more, including some hints of dynamic dispatch. I wanted to put this last one here, just to put up here. A lot of the things here that we built in Aptos Move, especially around parallelization, high throughput, building the scalability that you can build. Graphio was one of those good examples where we had millions of interactions with it. And using the sponsored transactions along with objects, parallelism through BlockSTM, we had huge, huge success. Look at all these pixels. You can see this is actually a time lapse over, I think, 24 hours of individual people drawing pixels, and eventually the bots got to it, which is why it's this beautiful mess of squiggles. But only on Aptos can you get this with the high throughput and also the building blocks that have come from Move. Come build with us. Thank you. My name is Greg Nazario. Feel free to follow us on Twitter as Aptos, or me and Greg Nazario on Twitter as well. Here's a link to our DevDocs page. Thank you, guys.